This is Adel Gastli. I'm going to present to you part 7 of the chapter about transformers. In this part, I will cover the three-phase transformers. A three-phase system is used to generate and transmit bulk electrical energy. And three-phase transformers are required to step down and step up voltages in the various stages of power transmission and distribution. A three-phase transformer can be built in one of two ways: by suitably connecting a bank of 3 single-phase transformers, or by constructing a three-phase transformer on a common magnetic structure. A set of 3 similar single-phase transformers may be connected to form a three-phase transformer. The primary and secondary windings may be connected in either Y or delta configurations. There are 4 possible connections for a three-phase transformer, which could be Y delta, delta Y, delta delta, and YY. Let us consider a Y delta connection of three-phase single-phase transformers as shown here. On the primary side, 3 terminals of identical polarities are connected together to form the neutral of the Y connection. While on the secondary side, the windings are connected in series. A more convenient way of showing this connection is illustrated in this figure. The primary and secondary windings shown parallel to each other belong to the same single-phase transformer. The primary and secondary voltages and current are also shown in this figure, where V is the line-to-line voltage on the primary side and A equal N1 over N2 is the turns ratio of the single-phase transformer. Note that for a unity turns ratio A equal 1, the secondary voltage will be smaller than the primary voltage because of the delta connection on the secondary. As you can see, the secondary voltage will be equal to the primary voltage divided by square root 3. Therefore, this type of Y delta connection is commonly used to step down a high voltage to lower voltage. The neutral point on the high voltage side can be grounded, which is desirable in most cases. Other possible connections are also shown in this slide. It may be noted that for all possible connections, the total kVA of the three-phase transformer is shared equally by each phase transformer. However, the voltage and current ratings of each transformer depend on the connection used. For instance, the delta Y connection is commonly used to step up the voltage, while the delta-delta connection has the advantage that one transformer can be removed for repair and the remaining 2 can continue to deliver three-phase power at a reduced rating of about 58% of the original bank. This is known as the open delta or V connection. However, the YY connection is rarely used because of problems with the high exciting current and induced voltage. It was stated earlier that in the delta-delta connection of the 3 single-phase transformer, one transformer can be removed and the system can still deliver three-phase power to a three-phase load. This configuration is known as an open delta or V connection. It may be employed in an emergency situation when one transformer must be removed for repair and continuity of service is required. Let us analyze this situation and consider this three-phase transformer connection in which one single-phase transformer, shown in dotted lines, is removed. For simplicity, the load is considered to be Y-connected. We can draw the phasor diagram for voltages and currents as shown in this figure. Here, V capital AB and V capital BC and V capital CA represent the line-to-line voltages of the primary. V small ABC, V small VBC, and V small CA represent the line-to-line voltages of the secondary. And VAN, VBN, and VCN represent the phase voltages of the load. For an inductive load, the currents IA, IB, and IC will lag their corresponding voltages VAN, VBN, and VCN by the load phase angle phi. So in this case, the transformer windings AB and BC will deliver power PAB equal VAB IA cosine 30 plus phi, while PBC is equal VCB IC cosine 30 minus phi. If you let the magnitude VAB and equal to magnitude VCB equal to V, which is the voltage rating of the transformer secondary winding, and magnitude of IA is equal to magnitude of IC is equal I, which is the current rating of the transformer secondary winding, and phi equals 0 for a resistive load. Then in this case, the power delivered to the load by the V connection is PV is equal PAB, small ab, plus P small bc, this means on the secondary side, which is equal to 2VI cosine 30. While with all the three transformers connected in delta, the power delivered should be P delta is equal to 3VI. So considering these two equations of PV and P delta, we can write that PV over P delta is equal to 2 cosine 30 over 3, which is equal to 0.58. So we can conclude that the V connection is capable of delivering 58% power without overloading the transformer, of course, which means not exceeding the current rating of the transformer windings. Some of the three-phase transformer connections will result in a phase shift between the primary and secondary line-to-line voltages. Let us consider the Y-delta connection and its respective phasor diagram of the voltages as shown in this figure. Notice here that the phasors VAN and VA are aligned, but the line voltage VAB of the primary leads the line voltage VAB of the secondary by 30 degrees. So we can conclude that the Y-delta connection provides a 30 degrees phase shift between line-to-line voltages in the primary and secondary. It can be also shown that delta Y connection provides a 30 degree phase shift between line-to-line voltages, whereas delta-delta and YY connections have no phase shift in their line-to-line voltages. This property of phase shift in Y-delta and delta-Y connections can be used advantageously in some applications. As we have seen earlier for the single-phase transformer, the performance analysis of the transformer is conducted using the transformer equivalent circuit. Therefore, it is also important to find the equivalent circuit of the three-phase transformer in order to analyze its performances under specific operating conditions. So, if the three-phase transformers are practically identical and the source and load are balanced, then the voltages and currents in one phase are the same as those in other phases, except that there is a phase shift or phase displacement of 120 degrees between the different phases. Thus, the analysis of one phase would be sufficient to determine the variables of the two sides of the transformer. Therefore, a single-phase equivalent circuit can be conveniently obtained if all sources, transformer windings, and load impedances are considered to be Y-connected. The equivalent Y load can be obtained for the actual delta load by the well-known Y delta transformation. This transformation allows us to find an equivalent Y load connection representation of the delta load connection. This figure shows how this delta to Y transformation is performed. Notice that the phase voltage in the Y connection is equal the line voltage divided by square root 3, and the phase current in the delta connection is equal to the line current divided by square root 3. Notice also that the line voltage in the delta connection is VL equal to ILZL delta divided by square root 3, while the line voltage in the Y connection is equal to square root 3 ILZLY. The same line voltage expression should apply to the Y equivalent circuit as for the delta connection. Therefore, we can deduce that ZLY is equal ZL delta divided by 3. So in the delta Y transformation of the load impedance, the impedance in the Y connection is 1/3 of the impedance in the delta connection. The equivalent Y representation of the actual circuit is shown in this figure, in which the primary and secondary line currents and line-to-line voltages are identical to those of the actual circuit. Now, the equivalent turn ratio A prime of this equivalent YY transform is obtained by dividing the primary input voltage V by the secondary output voltage V over square root 3A. Therefore, the turns ratio A prime for the equivalent single-phase transformer, which is the ratio of the line-to-line voltages on the primary and secondary sides of the actual transformer bank, is equal to square root 3 multiplied by the turns ratio A of the single-phase transformer. Thus, we can represent the three-phase transformer with the single-phase equivalent circuit that is shown in this figure. This equivalent circuit will be useful if transformers are connected to the load or power supply through feeders. Up to now, we have studied the case of a three-phase transformer made of three single-phase transformers. Now we'll see the case of three-phase transformer mounted on a common magnetic core. A three-phase transformer can be constructed by having three primary and three secondary windings on a common magnetic core. Let us consider three single-phase core type units as shown in this figure. If balanced three-phase sinusoidal voltages are applied to the windings, the fluxes in the different phases, phi A, phi B, and phi C, will also be sinusoidal and balanced. If the three legs carrying these fluxes are merged in the middle, the net flux in the merged leg is 0 because the flux vectors are shifted by 120 degrees as shown in this phasor diagram. This leg in the middle can therefore be removed as shown in this figure. This structure is not convenient to build. However, if section B is pushed in between section A and C by removing this yoke, a common magnetic structure shown in this figure can be obtained. This core structure can be built using stacked laminations. Both primary and secondary windings of phase A are placed on the same leg. Note that the magnetic paths of leg A and C are somewhat longer than that of leg B. This will result in some imbalance in the magnetizing current, such as the mutual inductance between phases A, B, and BC will not be the same as that between phase A and C because of the different length of the mutual flux path. However, this imbalance is sometimes not significant. The advantages of such a transformer are: it weighs less, costs less, and requires less space than a three-phase transformer bank of the same rating. Its disadvantages are the magnetic current imbalance, and if one phase breaks down, the whole transformer must be removed for repair. At the end, I will show you one movie taken from YouTube at the address shown here and in the bottom of the description. This movie presents well through animation the principle of operation of a single-phase transformer and the construction of a three-phase transformer.
Transformers are capable of receiving AC power at one voltage and delivering it at another voltage. In this way, they help achieve better transmission efficiency while transferring the power over longer distances. In this video, we will go through the working and construction of a three-phase transformer by starting from its simplest form. The basic working principle of a transformer is simple: electromagnetic induction. According to this principle, a varying magnetic flux associated with a loop will induce an electromotive force across it. Such a fluctuating magnetic field can easily be produced by a coil and an alternating EMF system. A current-carrying conductor produces a magnetic field around it. The magnetic field produced by a coil will be as shown in the figure. With the fluctuating nature of the alternating current, the magnetic field associated with the coil will also fluctuate. This magnetic flux can be effectively linked to a secondary winding with the help of a core made up of ferromagnetic material. This fluctuating magnetic field will induce an EMF in the secondary coils due to electromagnetic induction. Since the turns are arranged in a series, the net EMF induced across the winding will be the sum of the individual EMFs induced in each turn. Since the same magnetic flux is passing through the primary and secondary coils, the EMF per turn for both the primary and secondary coils will be the same. The EMF per turn for the primary coil is related to the applied input voltage as shown. As a result, the induced EMF at the secondary coil is expressed as follows. This simply means that with fewer turns in the secondary than in primary, one can lower the voltage. For the reverse case, one can increase the voltage. But since energy is conserved, the primary and secondary currents have to obey the following relationship. Three-phase transformers use three such single-phase transformers, but with a slightly different coil configuration. Here, the primary and secondary coils sit concentrically. Two more such windings are employed in a three-phase transformer. Transformers with high power ratings generally employ a special kind of winding, known as a disc-type winding, where separate disc windings are connected in series through outer and inner crossovers. The low-voltage windings are connected in a delta configuration, and the high-voltage windings are connected in a star configuration. Thus, the line voltage further rises to root 3 times at high voltage side. This also means that, from a three-phase step-up transformer, we can draw 4 output wires, 3 phase power wires, and 1 neutral. High-voltage insulated bushings are required to bring out the electrical energy. The core of the transformer is made of thin insulated steel laminations. Such steel laminations are stacked together, as shown, to form three-phase limbs. The purpose of thin laminations is to reduce energy loss due to eddy current formation. The low voltage windings usually sit near the core. Various kinds of energy loss happens while transferring power from the primary to secondary coil. All these energy losses are dissipated as heat. So usually the transformer is immersed in a cooling oil to dissipate the heat. The oil dissipates the heat via natural convection. Oil in the tank will expand as it absorbs the heat. A conservator tank helps to accommodate for this volume change. To know more on different types of transformer cores and windings, please check out our other videos. Thank you.
This is the end of this part. Thank you for watching this video.